The title of my talk is Dynamic Clamp with the D-Patch Patch Clamp Amplifier System. I'm going to talk about bespoke experiments, customized experiments at the edge of technology. As I said, my name is Jan Dolzer. I'm the product manager for the patch clamp systems at Sutter Instrument. I'm going to give you a brief introduction about what dynamic clamp is. It's not something that was newly invented, but the D-Patch has the ability to take it to the next level. I'm going to talk about how dynamic clamp is implemented in the D-Patch system in particular. And then I will show you two scenarios in a live demo. One is eliciting action potentials by injecting current steps into a model cell. And then the visualization of the dynamic clamp current that in essence helps you monitor the experiments and making sure that what you think you apply to the cell is actually what you apply to the cell. And then I'll summarize and again explain what the advantages of the D-Patch system are compared to other systems that provide dynamic clamp. What is dynamic clamp? It's also known as conductance clamp, and it was first introduced in 1993 by two separate groups, Eve Marder at Brandeis and Robinson and Kawai in Cambridge, UK and in Japan. And since then, there have been quite a large number of publications with dynamic clamp. Here is one example from Astrid Prinz et al. Showing an aplasia neuron, action potentials from an aplasia neuron during a spike train. The initially relatively short action potential gets longer in the control conditions, and then this effect can be blocked pharmacologically by blocking two types of potassium channels, IA and a delayed rectifier potassium channel. And this pharmacological block can then be rescued by injecting the currents that these two channel types conduct using dynamic clamp, and then this initially short and then getting longer action potential, this behavior also occurs. So in this case, you can mimic currents, and that lets you explore what these currents would have looked like to begin with, either with a pharmacological block, or of course the same would be if you use a knockout mouse, knockout model. Another example how dynamic clamp can be used is by doing the opposite thing, by not injecting the currents as activated currents, but by using a negative conductance and mimicking the pharmacological block by subtracting negative currents. And again, this effect of the action potential getting longer in the course of a spike train is blocked, disappears as if it was pharmacologically blocked. Third scenario that I'm not going to talk about today would be mimicking synaptic input to a cell in a slice in a tissue sample. So let's look at the verbal definition of dynamic clamp. If we do voltage clamp, we inject and then also measure the current that's required to maintain a given membrane voltage. In current clamping contrast, we inject a fixed amount of current, and in dynamic clamp, we inject a current that is a function of the measured voltage, not a fixed amount, unlike regular current clamp. The injected current, in essence, is a conductance that is a function of the voltage, the membrane potential here, and we have to take the reversal potential into account, and if we set that to 0, then in essence that will be a leak conductance, a leak channel. But in reality, it's a little more complicated. We have the sum of all conductances as a function of the membrane voltage minus their respective reversal potentials. And this is the same equation. And if we look at one of the conductances that we typically have in a cell, a sodium conductance, that would be governed by an activation gate, in the case of a voltage-gated sodium channel that has 3 particles, and an inactivation gate H, that is only 1 particle. That leads to a series of differential equations here. I'm not going to go into the math. All I want to highlight here is the dm by dt, looking at the activation gate. It's a function of time, and that time, that dt, the time intervals, need to be both short and constant. That's important, no wobble. And that's the challenge Doing that with conventional electrophysiology systems is not that easy. Why is that? Because a conventional patch clamp system consists of an amplifier that puts out an analog signal that gets fed into a computer interface, and the computer interface is controlled by software. The software also puts out stimuli to the amplifier, but what's important is this connection is typically USB, and the computer typically runs on either Windows or a Mac machine. And those are operating systems that are not real-time operating systems. That means if you want to do dynamic clamp, you need those constant real-time intervals. That means you need to split up this computer into two computers, one that's responsible for data collection and the other one that controls the dynamic clamp and runs a real-time operating system so that you have the fast and consistent timing that you need to compute the current that you want to inject back. As I said, Windows or Mac are not real-time operating systems, so they can't be used. And you can't use a USB connection because all that introduces delays that are not only not under our control, they're also not constant. Hit this stage, the D-Patch ultra-fast low-noise amplifier system, and this is in essence something that looks like this. We have the head stage, then we have an interface, and then we have FPGA, a field programmable gate array, and also two ARM core processors in the system. They give you a lot of computing power, and they take the place of the dynamic clamp computer, the second computer that I had on the previous slide. So if we look at that here, on the D-Patch system, we have a head stage. We have an interface that's in the blue box, the preamplifier here. FPGA and ARM core are in the main unit, and the software runs on the computer. And that's exactly what I have. Before I forget, depending on the conductance model, this can run at update speeds up to 500 kilohertz. And that's not the sampling rate. The sampling rate is 5 megahertz, 10 times as fast. But the dynamic clamp current can be updated at that speed of up to 500 kilohertz. And what I have sitting on my desk here is exactly that. I have my D-Patch main unit. Then I have the auxiliary output 1 connected to the auxiliary input 1. And why that's important, we'll get to that in a minute. I have the preamplifier unit here. And I have the head stage with a model cell in cell setting. And I don't even need a whole lot of shielding. You're going to see when I switch to the software demo, there's not a whole lot of noise going on there anyway. The whole thing is controlled by SUDDA-Patch software. I'm not going to go into any details of the basic operation. As Telly already mentioned, we have a number of videos on our YouTube channel about that. I'll just briefly talk about dynamic clamp models, and we will use the Hodgkin-Huxley style gate model in the demos that I'll show. We also have a Goldman-Hodgkin-Katz conductance model and a Markov model. And then we have what's called variable conductance model. And again, in the interest of time, I'm not going to go into that today. One thing we are considering, the variable conductance model could be folded into the Hodgkin-Huxley style in essence with a constitutively open conductance. You can mimic that as well. So that may change in the user interface. I'm also not going to go into too much detail about the user interface of the dynamic clamp. That is explained in a webinar that we held last year where Greg Helmstedt introduced a lot, and I also lifted a number of slides from his presentation where he introduced quite a few aspects of the dynamic clamp and also explained the basic operation of the user interface in that area. That's available on our YouTube channel. The first scenario that I'm going to show you is elicited action potential, and I'm going to show that in both membrane test, and then we'll create an FI plot. In the membrane test, here's the membrane test window. We have our voltage signal, our current step, and here is the D-Patch control panel. And that looks a little complicated at first sight, but we really only need to focus on two components. One is up here, we are in current clamp mode, and that little flag shows that dynamic clamp is loaded. And the second one is here, the holding current. I'm injecting minus 250 picoamps. That is because my model cell is a passive model cell, just a passive ohmic and with a capacitance model cell that doesn't have resting potential, so I'm mimicking in essence a resting potential. If you do something like this to a real cell, that cell might not be all that happy, because keep in mind, if you inject a steady current, you're moving charges. That means you're changing the ionic composition in the vicinity of the cell. You're either depleting or enriching ions potentially, so you probably don't want to do that with a real cell. And then what I'll do is, with the Hodgkin-Huxley model loaded here, I will not use a constant holding conductance, but I will use what's called a conductance stream, where I can, in essence, change the holding conductance during my experiment using the deep patch control panel. And I'll explain that a little bit in the live demo. And then the second thing I'll do is I'll create an FI frequency over current plot, where I inject current steps of increasing amplitude and then look at the action potentials that elicits, and I'll measure the frequency and plot that in real time. The second scenario I'm going to show is synthesized voltage-gated sodium currents. I'll first create an IV plot, then I'll show steady state inactivation and recovery from inactivation, and in the interest of time, I'm probably going to gallop through the latter two relatively quickly. So here, looking at that, there will be the IV plot, here will be the steady state inactivation, and here will be the recovery from inactivation from a lengthy conditioning pulse here. The longer the interval is to my test pulse, the more sodium currents recover. Let me switch to software. SetUpPatch runs on Igor. Two components that we're going to work with, the dynamic clamp editor and the routine editor. And over here is the deep patch control panel. And first, as I said, I will run the membrane test, and I need to load. I'm going to load my Hodgkin-Huxley model here. This is in essence run continuously. I have three conductances, a sodium, potassium, and a leak current. Sodium has an activation and inactivation gate, as I explained before. And if I load this, the little flag here shows it's there, and then have a constant train of action potentials here. That is because my holding current hasn't been enabled yet, so let me enable that. And then we only get action potentials during the duty cycle of this 100 picoamp step. Over here is the amplitude. Only during the duty cycle I get action potentials here, and then I can play with the holding conductance. This is 1.2 microsiemens starts, and I can use the triple slider here. That's a control that we have in several instances in the deep patch control panel, where I have three sliders with different sensitivity, and I can reduce the conductance to the point where, what I should actually do is make the change here. The holding conductance was fixed at 1.2 microsiemens. I need to use the conductance stream in order to control that over here. So let me update the model. Conductance model has been updated, and now I should be able to reduce the holding conductance to the point where I only get a single action potential at around 1 microsiemens. And if I reduce it further, somewhere around 830, 850, I start seeing action potentials. And if I go high enough with the holding conductance, then eventually I'll get action potentials throughout the entire sweep of the membrane test. So that is just one example. This is my completely passive model cell here that, with dynamic clamp, fires action potentials. The second thing I was going to show you was running an FI plot. So here are my current steps of increasing amplitude. I'm recording the current and the voltage signal. Here is my stimulus out, and then in real time I'm plotting the frequency versus the segment amplitude here. And if I run this, it looks like this. Up here are my current steps, and down here are the action potentials. And here the frequency is plotted in real time, starting at about -200 picoamps. I get a relatively high frequency. And let me switch to the second scenario here. I have the derivative of the Hodgkin-Huxley conductance in essence. Let me duplicate that and call that dynamic clamp NAV. And what I want to do here, derive in essence from the original Hodgkin-Huxley model. I'm only interested in the sodium conductance here. I'm not interested in the potassium or the lead conductance. And then I'm going to use a different routine. This is a derivative of the sample routine IV. Let me highlight the main changes here for the input channels. Rather than using current and voltage, I'm using the auxiliary in. You remember I'm feeding my auxiliary out signal back into auxiliary in. I also need to derive my voltage signal from auxiliary out 3. And then I also have a virtual signal where I have the stimulus, that's the representative of my stimulus signal here. Then for the output signal, that is my voltage steps here. And for the measurements, I'm measuring the peak current, the absolute peak during the step, and I'm plotting that versus the command. And that gives us, of course, I also need to load this. I still have the Hodgkin-Huxley model loaded. And that, of course, does not give us a good sodium IV curve. So let me load the sodium IV and run this. And then what we're getting is sodium inward currents here. And again, this is my model cell, my totally passive model cell sitting on my desk, generating what looks like sodium currents that are governed by the conductance model, the Hodgkin-Huxley model that I have loaded. This can also be used for assay development. And let me just show real quick the other two. Back to the routine editor, the voltage-dependent inactivation. So what we see here is at the end of an inactivating, a conditioning step, we see the current activating more and more, but we also see it's bottoming out here at the beginning. That is because my holding conductance is too large. So let me put that 0.5 micro and run that again, and now it doesn't bottom out anymore. And we get the same thing. And very briefly, let me run the recovery from inactivation, executing this. So what we have here is our inactivating step, and then at the end of the step, the intervals between the step and our test pulse increase. And here again, I show in real time the recovery. And let me briefly summarize the advantages of the D-patch system. We have a powerful dynamic clamp engine with update rates, as I mentioned, of up to 500 kilohertz. You do not require any third-party hardware for that. That is a big advantage over other systems available. We have multiple conductance models that are supported. The synthesized current can be monitored, as I just showed you, and that can also be used for assay development. And we have dynamic clamp pools. I didn't go into that too much. That was in essence the conductances that I selected from. The data acquisition, management, and analysis software is integrated and included with the D-patch. The conductance settings are saved with the experimental data. Metadata are stored. Again, this is something that's in other presentations that we've done in the past, and there's powerful analysis tools available.